I don't see anybody else in the waiting room, so I think we can start. So welcome everyone. Welcome to this edition of the seminar series organized by our technical committee on model-based optimization for robotics. It's a technical committee that is related to the IEEE Robotics and Automation Society. And if you want to know more about our activities, there is this web page that you can see here. We also have a mailing list. If you register to this mailing list, you can be notified to the next seminar series that we organize, as well as the Best Paper Awards and the other events that we are organizing. Feel free to either have a look at our website or to join our mailing list. And we are organizing this seminar series, and we have the chance today to have Ratliff with us. Nathan is the Director of System Software at NVIDIA. He holds a PhD in robotics from CMU, with a career path that spans both academia and industry. It includes the University of Stuttgart, Max Planck Institute, as well as Google, Amazon, together with his own startup, Lula Robotics. He is a founding member of the Robotics Research Group at NVIDIA, and he is now part of the group building the Isaac Cortex software, which is based on Omniverse and IsaacSim. And today, Nathan will be talking about the geometrical foundation of continuous control. And we are looking forward for your presentation. So we'll stop sharing and the floor is yours.
Yeah, so this talk is going to be on the geometric foundations of continuous control. One of my strong collaborators is Carl van Wyk, who I've listed here. And a lot of the experiments that he did here, we both came up with the theory for this and really fleshed it out over the last few years. And so I have them listed here. Okay, so do you see the panel on the side? Is it blocking the screen?
No, it's fine. It's fine.
Okay, cool. Yeah, so over the past 5 years, I've been at NVIDIA, started off in research, now pushing into the product area of trying to productize some of these things into what we call Isaac Cortex, which is a collaborative robotics framework for developing systems on top of the IsaacSim tools and Omniverse. And a lot of this research came from the Seattle Robotics Lab, and we're still continuing to develop it. And what you see here is a series of demos that we gave. In the collaborative robotics area, reactivity and real-time processing and reactions, state estimation, adaptation, and stuff like that are all critical because the world is constantly dynamic. Things are happening. Even your estimate of the state is changing based on the current changes in the belief and stuff like that, and the information that you have. So these systems that we develop are fundamentally reactive. And what I'm going to be talking about today is some of the underlying technology for developing policies for continuous control that are both expressive, programmable, can be trained, and can contain a lot of information. That's the real crux of all of this stuff. Oops. There we go. But one of the perspectives that I've started moving toward over the last, especially the last year, has really been shaped by this monograph that Bertsekas put out last year. And so I want to point everybody toward it. It's really kind of transformational in the way I think about this stuff theoretically. This monograph is Lessons from AlphaZero, where he looks at the history of dynamic programming and reinforcement learning and what's worked in systems, especially looking at case studies like going back to Saro's backgammon program and AlphaZero and stuff like that. And what he shows is that these policy iteration algorithms, especially the type that AlphaZero employs, where you do forward search on top of this actor-critic network to create better actions and better value estimates, and then basically project those that data onto a class of actor-critic networks. That's actually running Newton's method on the Bellman equation. And this sort of theory spans discrete actions, discrete spaces, and continuous action, continuous spaces, and kind of the entire spectrum of abstract dynamic programming. And so for continuous control, the theory itself is very applicable. And in continuous control, we often do optimization, model-based optimization, do a lot of computation to find a good local minimum for the thing, run optimal control over horizon and stuff like that. And for a lot of problems, especially kind of more local problems, that actually works really well. But what we see from this theory is that that is effectively a single Newton step on the Bellman equation, starting from, in many cases, just starting from 0. And if you think about Newton's method, like you would actually want to take many Newton steps in order to kind of get us to a good starting point, and then online take another Newton step from the current state to get good proficient online behavior. And he shows that for like AlphaZero, that's the difference between a good chess player and a world-class chess player. If you kind of like start from a good starting point, it captures a lot of information from past problems that it's solved, but doing that final optimization online gets you to world-class performance. And so what this tells me for continuous control has traditionally been more difficult than discrete spaces, discrete actions, discrete states, and stuff like that. But it's still fundamentally the same problem. And the literature that Bertsekas put out, like in a series of books leading up to this, really kind of characterizing this notion of abstract dynamic programming, really captures the similarities between all of these methods. And now with this latest monograph, kind of really characterizes what we can do as effectively running these solver algorithms on the Bellman equation, which include Newton's method on the Bellman equation. But that tells me like this is just part of the fundamental theory of optimal control for continuous control, and we should exploit it in some way. And the major challenge here, the major question, which I think we need to address, is how do we effectively encode information into continuous control? So like if we spend a lot of effort doing optimization to get good actions and good value backups, instead of throwing that stuff away, how can we take that information and encode it in a way that can be leveraged in the future? And that would give us the tools to be able to run these sort of Newton methods effectively and robustly for training, continuous control, and ultimately executing at inference time these policies. And so that's really the question I'm addressing here. And we're taking a geometric approach to it, kind of like look at the geometry of continuous control and see how we can exploit that to better represent policies and encode information into them. I don't know if you can see this video very well. It's moving pretty fast, but if you can't, there's a website linked up here that you can go to, which has the video. But the theme is that we're going to exploit geometry. And our hypothesis is really that much of continuous control behavior is actually geometric in nature. And from kind of what you see here, you can kind of see what we mean by that. Moving between these cubbies, it moves between paths that are really geometric in the sense of you can speed up and slow down the system, and the basic path that it needs to follow to move around these cubbies and into and out of these cubbies and stuff like that shouldn't really change. The behavior of the robot is largely independent of the speed that it's traveling. And so like there's this network of paths that's defined by both the robotic structure and the environment around it that really influences the robot's behavior. And that's what we're going to be building out and exploiting here. And that sort of observation has been used quite a bit in planning systems. Like most planning systems, if you run an RT and then smooth it and stuff, you often get not a trajectory out, but a path, which is just a series of points that the system has go through. And then there's a separate retiming phase where you actually speed it up and slow it down along that direction of motion, along that path. So it creates a particular velocity profile for following that. But you can choose any sort of velocity profile that you want. You can speed up the robot, you can slow it down, you can make sure that it doesn't jerk too much and all that stuff. And that's independent of the actual like path generation problem. And so far, like planning systems have done that to generate single trajectories or single paths and then turn them into trajectories. But typically policies don't represent their behavior in the same sort of way. But you can kind of see from this anecdote here, this just moving between the cubbies, that this notion of being able to follow paths and being able to represent behavior as a series of paths that are affected by the environment and the robot's kinematics and constraints is something that we might be able to exploit as an important inductive bias. So how do I get there? We go. Okay, so that was the little introduction. The rest of the talk is going to cover three main sections. One is just describing geometric fabrics, which is this structure that I've been describing of how we can exploit geometry to represent behavior better. And then talk about some particular mathematical tools for exploiting the structure of these things, which actually play into how we design systems, real-world systems, leveraging this theory. And then finally, go into what we call neural geometric fabrics, which is a way of representing the geometric fabrics as neural networks, leveraging that inductive bias of geometry and the structural tools that we define in section 2 to create structured policies that are both flexible in their representation, but also extremely data efficient because they exploit this geometric prior. One note is some of the stuff I go into here is fairly heavily mathematical. And so we have some background material, which you can take a look at, including some lecture notes that I made on the geometry of smooth maps, some notes that we wrote and published in ICRA on generalized nonlinear, what are spray geometries of paths, and Finsler geometry that kind of leads to geometries of paths, as well as the geometric fabrics work. And so I encourage you to take a look at that background material. And if you're not following the math right now, just focus on the intuition. The intuition is actually fairly visual and straightforward to follow, I think. So the high level of geometric fabrics is what we'll see is that all dynamical systems of a robot actually have an underlying geometry associated with them. And when I talk about geometry, I'm not referring to like a polygonal mesh or kind of a structural geometry or something like that, but this generalized notion of a high dimensional geometry as forming a network of paths for the system. So you can imagine this in C space. If you just imagine this kind of like bundle of paths that exist, where any position of velocity from that kind of extends a path where you can kind of move along that almost like a little tunnel that you're moving around. And kind of if you shift that initial direction that you're moving in, the system runs along a very similar path, but slightly different, and you kind of like shoot out of a single point in all different directions, and it moves along different paths. And you can kind of see an example of this here. This is a very simple two-dimensional problem. There's an obstacle here, like 3 obstacles here in purple, and there's a point right here, which is the starting point, and we shoot integral curves out from all different directions, and we look at how they bend around obstacles and stuff like that. And each one of these is a different path that the system might follow. And so these geometries are often called spray geometries because they're characterized by how their paths spray out of a given point, just like this. So this road network of paths defined by the geometry is really going to define the prior on what the system wants to do. And a geometric fabric is a combination of this road network of paths along with the energy that's conserved. So the system isn't naively like speeding up and slowing down in some weird way, or kind of like growing to infinite energy or something like that. But it has this conserved energy, so you can think of the system nominally as just moving along a path at a constant velocity. And that's what forms what we call a geometric fabric. And in the absence of anything else, any like forcing policy, the system just wants to follow one of these paths. And so the system will just kind of move at a constant velocity along one of these paths infinitely and just kind of stay there. But then the question is like, how can we leverage that network of paths to actually accomplish a task, like reaching a point like this? And that's where a policy comes in, where the policy's goal or job is to really drive across this network of paths to both speed it up and slow it down along the direction of motion, like slow it down as we get close to this target here, so it can come to the stop, but also to push it orthogonally to the direction of motion to steer it along the way, so it moves from one path to the other. So you can think of the policy as really like shooting off in the right direction, getting onto like the interstate highway, and then travels along the interstate highway. And then when it gets close to its goal, it kind of like exits from that thing and tries to steer it toward the target. And what we'll see is this policy quite literally breaks into two terms, one which is energy regulation, kind of speeding it up and slowing it down, and the other one which is entirely orthogonal to the path, which just literally steers it. So you can think of it as quite literally driving across this network of paths. It has a little steering wheel, it steers along, and it speeds up and slows it down. And what you see here is an example of all of this. Like the geometry wants to do its own thing, but we have a policy over the top of it that's attracting it toward that goal and also regulating energy so it comes to a stop at that point. And along with that also comes what is called a system metric, which defines how easy or hard it is to push it off a path from in a given direction. The system metric is a positive definite matrix, which has eigenvalues in different directions, defining how difficult it is to kind of either speed it up or slow it down or kind of make it deviate from the path in given directions. So like here, it should be difficult to push it into the obstacle, but right here, it should be easy to steer it around because there aren't obstacles in the way. And so the system metric regulates that level of difficulty of pushing the system around. And so the geometric fabric, which consists of this energy and the geometric paths, as well as the system metric, really define a prior on how the system can navigate this sort of thing. So to get some intuition for these geometry of paths, here again is both the video that I was showing before, but also a two-dimensional representation of some of these things. And so what you see here on the right is two rollouts from any given point of a geometric differential equation, which is just trying to avoid this obstacle here. And both of the rollouts start at the same point and start in the same direction, but have two different velocities as represented by these two arrows. And you can see that despite one of them moving more slowly, they both always follow the same path. And so that's the notion of geometry. It's independent of how fast you're going. The path that the system travels along is entirely defined by the initial direction. And we can get some intuition for what are the requirements on a differential equation to have this property of path consistency by looking at just the nature of finite differencing and how velocities and accelerations differ from each other. So if we look at a curve here and look at 3 consecutive points and say that they're separated by delta t apart, we can take finite difference estimates of the velocity and acceleration for these things and write out what the equations would be. This is just the finite difference velocity. This is the finite difference acceleration here. And one thing you notice is that the velocity depends on 1 over delta t squared, or delta t, and the acceleration depends on 1 over delta t squared right here. And so we can ask, like, if we speed up the system by scaling the velocity by lambda, how does that affect the acceleration if we want to stay along this path? We just do a little algebra, move the lambda over to the delta t, or I just combine it with the delta t, and then plug it into the acceleration, and we see that if we scale the velocity by lambda, then the acceleration has to scale by lambda squared in order to stay along the same path. And it turns out that any differential equation that has this property, where you scale velocity by lambda and the corresponding acceleration scales by lambda squared, is called homogeneous of degree 2, and you can prove that it's path consistent in this sense. And so the fundamental starting point for defining a geometry is just defining a second order differential equation of this form, which is homogeneous of degree 2, which simply has the property that if you scale velocity by lambda, then the acceleration is scaled by lambda squared. And so path consistency really comes from this homogeneous degree 2 setting. And what we'll do is construct differential equations by just giving them this homogeneous degree 2 property and then speeding them up and then slowing them down in the right way to conserve some energy. And that energy conservation thing is what we see here. Kind of the second part of constructing one of these things is choosing an energy. So here I write Fencer energy, and in the paper we wrote about nonlinear geometry and Fencer geometry, we kind of define what that is. But for these purposes, you can think of it just as like any classical mechanical energy. That energy comes with its own equations of motion, just like classical mechanical equations of motion are derived from classical kinetic energy, just using the Euler-Lagrange equation. So if you start with some energy that you want with corresponding equation of motion, you can derive specifically how you might speed up and slow down along the direction of motion in order to make this system conserve an energy. And we have some theorems around that and some formulas, and that we call energization of the system. So if we write down any homogeneous of degree 2 differential equation, which has this path consistency property, and then, quote, energize the system so that it conserves a measure of energy, then what we end up with is this nice differential equation that has the same set of paths, because we're just speeding up and slowing down along the direction of motion, but it has this concrete measure of conserved energy, which means that any system that's running over the top of this, if it does nothing, it's just going to conserve the energy. If it just steers the system, it's still going to conserve the energy. And if it speeds up and slows down, it's going to be able to modulate that energy, increasing the energy and slowing down the energy as it needs to. And also, if we just stop, if we stop doing anything and just damp the system, we're always going to come to a stop. We're going to bleed off this energy and come to a stop. And so these homogeneous degree 2 foundational systems that are energized to conserve this energy form this fundamentally stable foundation of a differential equation system, which systems can run over the top of and regulate their energy in a nice way. And the underlying system itself isn't going to make the system explode or do anything like that. It's just going to influence the behavior by influencing the path that it wants to follow. One connection, which I'm not going to go into in too much detail, but is in some of the background literature, is that all mechanical systems, all control systems really have one of these underlying geometries. And in many cases, those geometries aren't useful And so we, in a sense, have to invert them or wipe them out to actually get good behavior. In some cases, they are useful for the task. And when they are, we see massive sample efficiency gains from this. So an example to start off with is torque control. If we have a torque control policy running over a mechanical system, the mechanical system itself, you can show that that's actually a Riemannian geometry, but the geometry is not really useful to the task. The geometry is literally the set of paths that the system wants to move along based on its inertias. And it tends to be like arms swinging and doing various things that have nothing to do with the task. And so if we build a policy over the top of that, a torque control policy, that policy basically needs to fight against that mechanical system to get the system to corral into whatever task that it wants to do. And so in many cases, we actually just wipe that out using inverse dynamics control and replace that Riemannian geometry with what's effectively a Euclidean geometry in C-space. So in C-space, we end up with these like straight line geometries and kind of manifests as like the joints become independent of one another in terms of like the paths that they want to follow. And in that case, we wipe it out and give it a clean slate, but still like a policy that we build over the top of it has to build all aspects of the behavior into that policy, including basic things like moving the end effector in a straight line or kind of like getting it to go to a goal and stuff like that. And so in many cases, these days in reinforcement learning and imitation learning, systems are built on top of operational space control and actually just control the end effector, because operational space control not only wipes that previous geometry out, that underlying mechanical system geometry, but it replaces it with a useful geometry, which tends to want to make the end effector move in a straight line. And that operational space control Euclidean end effector geometry tends to be a useful prior for many different tasks, because in many cases we have to like grab something, we have to insert the end effector somewhere and stuff, and kind of like having a bias of just moving the end effector in a straight line is kind of the right starting point for a lot of things. But operational space control dates back to the 80s. It's kind of just a basic tool that we have this observation where, like, you know, it solves a big portion of the task. A lot more information could actually be encoded into these geometries. And when you are able to encode into the geometry things like collision avoidance, posturing of the arm, how the end effector approaches a target and stuff like that, you end up with the ability to create like what are essentially extreme data efficiencies or extreme sample efficiencies for optimization and learning here. On the top, you see just some behaviors that we developed with this stuff, just hand designing the behaviors over the top of some of these things for a particular demo. On the bottom, you see actually an optimization system running over the top of some of these geometries, where we literally just optimize a single waypoint that it wants to go through. And so we can do these longer horizon planning-based tasks. And the optimization converges really fast. It's stable, and it's able to leverage all of this underlying geometry. So I mentioned a big part of this is forcing a geometric fabric, building a policy over the top of one of these road networks of paths so you can actually get the system to accomplish a task. This is just a visualization of that based on the example from before. What you see here on top is actually literally the road network of paths that come from the geometry. So here we start from this point, we shoot out a spray of integral curves. These form a series of paths that the system wants to follow that are independent of the speed that it follows. And they tend to move around obstacles, get attracted toward the point, but they don't slow down the right way. They don't exactly hit the point. They just kind of loop around and stuff like that, because we're just looking at the basic underlying geometry. The system wants to be attracted to the point, wants to avoid obstacles, but it doesn't really have the goal in mind. And so by placing a very simple policy over the top of it, which just regulates the speed of the system and nudges it slightly toward the goal, we can corral it very easily to both leverage that geometry and get to the target that we want. And in equations, this looks like this sort of thing. So we see here, we start off with this path consistent homogeneous of degree 2 differential equation, which is just any differential equation that has that homogeneous of degree 2 property. This speed regulator here is part of the energization process. So we speed it up and slow it down in the right way so it regulates its own energy and maintains constant velocity under some metric of velocity. And we have specific formulas for calculating the alpha for that. And then over the top of it, we place a policy, which behaves very similarly to the types of policies we would place over like dynamical systems for the underlying simulator or physical system. The interactions between the two are actually entirely analogous. But geometrically, this policy acts to do two things. One, speed up and slow down along the direction of motion, and two, steer the system so we can bend from one path to the next. Here's an example of some of the behavior that comes from this stuff. And in this initial experiment, it compares the geometry versions, these geometric fabrics, to versions where instead of being geometric, they use things like potential functions and stuff. And kind of superficially, what I described sounds similar to like local potential functions, but the geometry of this is very, very different. And you can see that under different speeds, geometric fabrics end up being entirely path consistent, whereas using something like potential functions has very different type of behavior and has like significant oscillations that occur at different speeds and stuff like that. So let me play this video. There's a little animation of that in the beginning, kind of showing how that stuff plays out. And so our takeaway from these things is as much behavior as possible should be actually written into the underlying road network, these geometric fabrics, so that we get this path consistency and consistency of behavior as we speed up and slow down. Here's a comparison between geometric fabrics and or earlier RMPs. We get closer to constraints more easily because we're representing these geometries in a nice way. This one, sorry, that's pretty fast, but you can see it going through. The video is online from that link, but you can see it going through the ring, and there we go. There. Geometric fabrics is able to get through these very tight constrained quarters, but RMPs, which rely more on kind of heuristically defining these differential equations and using potential functions, has to be more conservative because it's not leveraging geometry in a nice way. Here's an example where it's just throwing a bunch of obstacles at the system. Geometric fabrics does a lot better at navigating all of these obstacles, just kind of slipping around these things and actually getting to a target. Whereas you'll see at various points, RMPs are just getting kind of bogged down by all the constraints in the space. And this is just the example I've been showing where what we did here was really write most of the behavior that you see into the geometry of the system and then just have a very simple driving policy that drives it to the goals. Okay, so now let's go over a couple structural tools for how to exploit this. Because of the time, I'll go a little bit faster through this material, but there's a lot of papers online that I point to. So in real-world systems, what I've showed so far is mainly just defining these things in C space and stuff, but real-world systems have a lot of different task spaces which we can try to exploit to kind of capture the structure of the problem. Examples are the locations or poses of the end effector or the different links, distances between those points and points in the space, as well as like a distance between like the end effector and a goal and things like that. And ideally, in designing systems, we'd exploit all of that structural geometry in a nice way. And it turns out that there's some nice set of tools for leveraging that within this framework of geometric fabrics. At a high level, we can just think of these different spaces as forming a tree of different spaces linked to their parent via just a differentiable map. So like if we start at the C space Q, there's a differentiable map to, say, the end-effector space, or a differentiable map to a link, and then different differentiable maps from that link to distance spaces to obstacles and stuff. And so we end up with this tree of task spaces. And kind of construction-wise, like how we would construct this sort of differential equation is we would place little pieces of the differential equation at each one of these spaces, and then do a series of operations to transform them back to the root. And so these little pieces of the differential equations are called what we call spects, short for spectral semi-sprays. And they live in each one of these spaces, and they themselves represent a little differential equation of this form. So far, I've really been describing just differential equations that are like acceleration equals some function of position and velocity. But it's important to represent them here in this form where we actually pull out this system matrix. And you can think of this as entirely analogous to classical mechanics, where you have this equation of motion. You can solve for what the acceleration is, and you can see like what the integral curves are from that. But it's important to keep them in this form here so that we can explicitly look at what the mass of the system is and what forces are being placed on the system. And that'll help us combine these little parts into bigger differential equations and do the trade-offs in the right way. And so some operations that we can apply to this are, on a given space, if we have many of these little specks, these spectral semi-sprays, we can sum them all up. And the summation operation is pretty straightforward to derive, and it ends up just being kind of a summation of these parts. But the cool thing is, if you look at what the resulting summed differential equation is, as in this H form, which is the acceleration form, you have to solve for what the acceleration is by inverting the metric and stuff like that. But you end up with this expression here, which is literally a metric weighted average of the individual parts. And so by summing things this way, we end up taking a nice metric weighted average of the little pieces. And so intuitively, we can define these pieces of differential equations by defining how we want the system to accelerate as this little part, and what the system should care about, which is the little metric piece. And then summing these things ends up just being a metric weighted average of those different considerations. And then we have another formula for pulling back the resulting differential equation into the C space. I'm not going to go through the derivation here, but in the next slide, we'll see kind of some properties of this, which make a little more sense. But the whole operation ends up being place some little pieces of differential equations on the leaves, pull them all back to the root. We end up with a bunch of little pieces of differential equation in the root, and then we just sum them up on the root. And that summing ends up being a metric weighted average of these little parts. And that ends up giving us this nice set of tools for reasoning and dealing with complex differential equations in these real world systems. So this gets a little bit into weeds, but if you're familiar with some of the geometry, there's this notion of covariance and covariant transforms. It turns out that these transform trees and the pullbacks that we do are inherently covariant. And so we don't even have to think really about standard notions of covariance, which get really complicated in the literature and stuff. We can just define these different equations on these transform trees, pull them all back into the root. They're inherently covariant, and then sum them up and all that stuff. And you can show that all of this stuff is equivalent to some of the standard least squares formulations that we see in the control literature. And so all of this mathematics comes from similar areas, and there's a notion of optimality in these operations. But we can also derive all of these operations just by, like the pullback operation, for instance, by looking at the definition of covariance and desiring covariant transforms for these things. Yeah, I think that's all I want to say on that side. But this makes it really nice to derive systems by just defining the spaces where different pieces of differential equation can live, and understanding that like there's going to be consistency across the pullback of that into a root space. And if we need to change parameters and stuff, like from one rotational parameter to another, quaternions to exponential map, for instance, we can just add a little differentiable map that corresponds to that change of parameters and just further pull that back into the new parameter space, and we end up with consistency of behavior because of these nice covariance properties, or which can also be looked at as the optimality properties of these equations. Okay, so this, based on those operations, we can, it's really easy to design a complex differential equation in parts by first kind of starting off with like a baseline geometry and then layering over the top of it different constraints that are imposed by different things in the system. And this diagram here shows an example of that, where across the top, you see kind of an increasingly sophisticated geometry being built up. And across the bottom, you see the forced version of that geometry, where we're forcing it to a target. So the bottom has a policy running over the top of the geometry. The top one just shows an example of the road network of paths that are constructed. And what we see from left to right is we start off with just a very simple Euclidean geometry, where it's just a straight line from a point. And then we incrementally add more sophistication to it. So here we add some joint limits, where we say like the system can't move past some barrier constraints. Here we add an obstacle, and we make the system bend around the obstacle. Here we just very generally add some vortices that are described as different geometric terms, where the system now just kind of wanders around based on the influence of these little vortexes that are represented by these circles. And then finally, we add a little bias geometry that pulls it, kind of biases it toward the goal. And we see it kind of wandering also toward the goal in a nice kind of like directed exploration way. But if we put the policy over the top of it, in all of these cases, we see the system nicely converging to the target. We see it kind of like just starting off with Euclidean, converging to target. We add the joint constraints, does the same thing. We add this obstacle here, and now bends around the target and gets there. We add these vortices, and it still gets to the target. And we add the kind of attractor geometry to the thing, and it does a better job of kind of beelining to the target at that point. And this kind of emphasizes one of the key properties of the geometries. The geometry itself doesn't bias the system in the sense of if the system comes to a stop, it won't be pushed by the geometry. The geometry is just a set of paths. And so for any policy that we put over the top of this, the policy has entire authority to get the system to do anything, to get it to converge to a particular target and stuff like that, or arbitrarily close to a barrier, because the underlying fabric is influencing the behavior, but without kind of like creating a concrete bias away from any given target. And here's another visualization of that, where we actually show it happening on the robot itself. We start with just like straight line motion. It's just wandering around in joint space in straight line. We see kind of just wandering aimlessly like that. We can add some joint limit constraints, where now it tries to stay away from those joint limits. At the end here, it actually converges to one of the joint limits. We can add a postural geometry, where there's this nice kind of collapsed posture that it wants to get to. It continues to move because it's conserving energy in that way, but it's biased to be around that sort of thing. Now we're attracting the gripper to a point right at the base, and then down here, we additionally add obstacle avoidance or body avoidance to that. So it's also attracted to the base, but it tries to stay away from itself. And then we add an obstacle to the whole thing. So it does the same thing. We'll try to avoid that obstacle. And finally start moving the target around. Right here, you see it oscillating around the target point because this is still just a geometry. There's no actual optimization potential over the top of it or policy. And the final version, we add the policy, which can regulate the energy, speed it up and slow it down. We get this very nice behavior around the obstacle. And you notice as it moves around the obstacle, because of like the joint posture, it keeps like moving back toward a good null space pose. And so it can run like this forever. And here's an example comparing RMPs on the right, our previous version of this, to geometric fabrics. And we can see that geometric fabrics are just much more snappy and well-behaved. I'm going to skip this one in lieu of time, but these are some videos showing the interactions with classical mechanical systems. I encourage you guys to take a look at this paper here, which shows that geometric fabrics are actually just a very natural generalization of classical mechanical systems. And we actually develop simulators that integrate classical mechanics into the geometric fabrics and can have interactions with it. Okay, really quickly, I want to go over these neural geometric fabric results. This you can think of just as a trainable version of geometric fabrics, which kind of connects us back to what I talked about in the beginning, where we want to exploit this structure, but we want to do so in order to encode information into it as effectively as possible. And so we ran some experiments with a trainable version of these things, where we gathered data using this DexPilot system, which is a just teleoperation system where we can do very dexterous manipulation based on remapping human hands to the dexterous hand. Collected a relatively small amount of data, 80 C-space demonstrations in this case, which are entire trajectories, and compared the sample efficiencies of a number of variants of these algorithms, including a couple of variants of neurogeometric fabrics, RMPs. These are the Riemannian motion policies, the previous version of this stuff, LSTMs, which are pretty standard in the literature, and generic neural networks. And what we see consistently is that geometric fabrics constitute a very well-informed but flexible inductive bias for continuous control. And so these things are able to learn from a very small amount of data, complex policies. The problems that we look at are picking up a sugar box, kind of this interesting problem where we have to touch a point on the table and then move around a can and push the can over to that target. And then the location of the can and the location of the target change over time between different runs. And then another one where we extract a tool tray from this toolbox. The architecture has the basic geometric fabric structure to it. This diagram is a little bit complicated, but it's kind of the basic structure that I showed. The main thing to take away from here is just the learnable components. The learnable components include the system metric for each one of these little pieces of the differential equation that we're learning, a geometry network, which defines the basic behavior, and then a damping network, which can speed up and slow down along the direction of motion. And here's a video of this. This shows just some of the demonstrations that we can do with the DexPilot and the type of data that we try to learn from. And here's the 3 tasks on the deployed neurogeometric fabric. I think we give it 2 attempts to try to accomplish the task. And in many cases, it's able to solve this thing pretty well. In a second, it's going to show some of the baselines. But one thing to remember about these results is that this is all low-level continuous control done in C-space, and we're learning from at most 80 examples of this stuff. And so the baselines, like neural network especially, just aren't able to represent the policy very well, as well as LSTMs. RMPs and this end-effector version of geometric fabrics do a little bit better, but they still don't do as well as geometric fabrics themselves. Okay, with that, I think I will finish, and I can take any questions if there are any.
Thanks a lot for your presentation. So yes, we can open the floor for questions. So you can either raise your hand with the Zoom functionality or directly unmute and ask your question. Or maybe I will start with one question. So in your presentation, you presented several examples of behaviors that require to reach some target and also to avoid some form of obstacles. And sometimes you had these obstacles moving and sometimes they were static. And I'm not sure if I understand well what is changing in the approach. What does it mean in terms of recomputation? Maybe could you elaborate a bit on this aspect?
What's changing in the approach? So basically, whether the obstacles are moving or not is not fundamental to the representation. In all cases, we well, actually, there are different versions of these that have different representations of the obstacles. But like a number of the early examples just use primitives to represent the obstacles themselves, similar to what like optimal control would use or planning. But we really just need distance and direction to the nearest point. And so newer versions of this leverage like distance fields, voxelized grids, or ray casting or stuff like that. In all cases, the question is just how to get the information of like what is the closest obstacle in the space. And then once we have that, we can compute what the collision term is for a given point on the arm. And then we can take a bunch of points on the arm and pull them back into the root and compute the kind of summary of the collision votes, basically. Does that answer your question?
Yeah. I think the follow-up question I have is regarding this incremental aspect. So you showed us how to incrementally layer these behaviors, and something I was not sure about is it something that is recommended? Is it something that will help the system by starting like piece by piece and by adding some additional cost to the problem? Is it helping the system, or is it something that is optional as I'm not sure if I understood if it is required or optional.
Yeah. If you're designing these by hand, it just helps rein in the complexity of designing those sort of systems. And so like for the initial geometric fabric results and especially like the RMP results and stuff, like this is how we designed the differential equations. We started off with like a simple system and then just layered different pieces on top. And so one thing that people wonder about sometimes is like you look at the complexity of the differential equation like this, like how can you actually design that sort of thing? And it turns out to be just very easy to layer these things on top of one another because of the nice covariance properties of these and the optimality property of the pullback. And so really it's about reining in complexity. If you train this thing, we don't do any of that stuff. We just kind of describe the different spaces, architect the learnable pieces in each one of those things, and then just train the whole thing jointly from the training data, because it's able to weed through those details. That said, one of the advantages of this sort of mathematics is that you can take pieces of this, which are common across many problems, and then specialize it to those problems by adding more layers on top. And so if you learn one component, which is kind of a foundational differential equation that maybe has all the constraints that I described before, joint limit avoidance, posturing, obstacle avoidance, getting to the target and stuff like that, you can additionally, on a new problem, which maybe like has to approach the target in a particular way, or you use this stuff to kind of like push an object or kind of pry something, just layer a piece over the top of that. And then leverage that entire prior that you learned from the previous experience. So that's some of the advantages of being able to layer these things in a nice way.
I see. Thanks. So questions from the audience?
I would have a question. I'm Johannes Engelsberger from DLR. Thanks for this super nice talk. So if I understand right, these geometric fabrics, they're like mainly geometry based. So basically kind of like groups of trajectories, as far as I understand. So my question would be, how do these system metrics that you talked about, how do they relate to kind of stiffnesses, or like what kind of interaction behavior do they correspond to? Like if you touch one of those robots and push it away.
I see.
That relates.
There's another aspect to this, which I didn't talk about, is how you translate this fully to control. In many cases, we use a standard incremental trajectory generation type technique, which is similar to DMPs and stuff. So you have this differential equation, which is just integrating forward a trajectory, and we pass it to a controller that can just follow that in a nice way. And that's actually, it has its disadvantages because, you know, it kind of loses some of the metric information for that, but it has the advantage of all OEMs tend to have that sort of interface. And so we can kind of interface this thing to a number of different robots. But we'd like to see, and we've started developing some ideas around, is leveraging that metric behavior in the impedance matrices of impedance control.
Yep.
Because these metrics define literally like how difficult it should be for a system to push into an obstacle, or like a policy running over the top of this, like how difficult is it to kind of like change the behavior. And ideally, that would actually be an impedance control. So we have strong impedance in directions that are toward obstacles, and kind of lighter impedance in directions orthogonal for that. We kind of get this to an extent by the way in which we handle kind of perturbations these days. Like if somebody pulls on the robot, we actually have the underlying differential equation shift in the right way. So instead of just using impedance control by itself, we look at the difference between the actual configuration, the desired, and actually explicitly add a new differential equation component that pulls it in that direction. So what we'll see is kind of like the system being pulled, and it starts back from where it ended up and stuff. But it also means that that's differential equation part that's trying to push toward the actual configuration, like if it's being pushed to an obstacle, would have a more difficult time doing that. And so it'll try to kind of like keep it out of there and just use the impedance controller.
Yeah, cool. Thank you so much.
There is a question from Max Span, but don't dynamic obstacles violate the consistency of paths? Does that harm the guarantee on convergence?
Yes. And I've actually seen some of that work, and I think it's really good. Ideally, we should have those things as part of the theory for this stuff. In this version of the work, we didn't flesh that out. Instead, use just the reactivity of these things. In most cases, for the types of systems that we're looking at, we can view the dynamics of the system as, or the dynamics of the obstacles as just kind of transient behavior, because the system is trying to grab something, or trying to open a door or something like that. And the convergence properties aren't really affected by assuming zero velocity there. But what we have seen in the past, and with especially like early implementations of RMPs, we looked at obstacles, not just like the distance space, but how that distance space changed. And so like there's a velocity component to that distance space, and we can react not only to like coming toward an obstacle, but if the velocity over the obstacle moves toward the arm, that velocity has significant velocity now in the distance space toward the arm, and the arm will react to it. And so like an obstacle kind of coming toward it will react to the system. And I think that sort of augmentation is super useful for real world systems. In a lot of this work, we kind of brush that under the rug, and we don't deal with it. But I think that's an important aspect to it. In terms of convergence, we don't really typically see issues with that in practice, just because like all of the spaces that we are currently caring about are stationary. But certainly, like if people are moving targets around and stuff like that, and the system has to track it, then we should take that into account.
Okay, thanks. Other questions?
So I have a question. Thanks for this great talk. I was wondering if this kind of mathematical framework could be extended towards the control of under-actuated systems or legged robots.
Yeah, it very much can. I think the best way to see that is in the connections here with classical mechanics in this paper. And what we find is that all of this stuff is about adding together different pieces of systems. And if one of those pieces of systems is literally the classical mechanics of the robot, then what the classical mechanics want to do, including like in the underactuated degrees of freedom, gets averaged into to the differential equation. And so we can put those together, we can derive some results in terms of like what that looks like in the underactuated space and stuff, and try to parameterize that. We haven't pushed too hard into that direction, but this paper here kind of fleshes out the theory behind it.
Okay, thank you.
Like, will some of these tools be available in the NVIDIA Isaac? Is it in Cortex, in Isaac, in Orbit? Like where can we find this to try this?
Yeah, we're putting together some tools, especially around the neurogeometric fabrics and vectorized versions of these things right now, and hopefully with the next release we'll try to get those things out. That specific deadline or date is flexible because it depends on how well we're able to flesh it out. But we are putting together some of these things so we can actually try it out, and especially Cortex and stuff. Cortex is this entire system stack where at the lowest level or the bottom layer, there's a series of policies which have command APIs that are exposed, and a decision layer at the top of that help like sequence those things and kind of reactively choose which policy to employ when and stuff like that. And the goal is to be able to train policies and interface it with that layer. And one of the major roadblocks right now to being able to leverage reinforcement learning for like not just research, but like industrial tasks and stuff like that is the consistency of training and the reliability and safety of the resulting policies. And what we want to do with geometric fabrics is to kind of create this underlying behavior, which is almost like a protective jacket that prevents it from running into things, gives it kind of like these underlying behaviors like posturing and joint limit avoidance and stuff like that. So reinforcement learning over the top of it can be more stable and safe. And so that's the goal. Hopefully soon we'll have some stuff in Isaac Sim. The exact timeline I'm not entirely sure about, but we're trying to push it out pretty soon.
Looking forward to it. Thanks. So I think the question is here. So maybe for the other participants, the question is, so when you are defining a geometry in a task space, for example, the distance between robot and obstacle, you would pull that into a higher dimensional space, usually configuration space. The pull metric is usually not full rank, then it is not invertible. How would you practically deal with such situation? Or do you rely fully on the fact that you have multiple geometries combined?
Yeah, it's all about multiple geometries combined. Typically, we don't resolve the differential equation until the very end. So if we look at something like this, or here, the spec is defined in terms of not the h, which is the inverted or resolved acceleration, but the forcing term. And so we can have little pieces of the differential equation in lower dimensional spaces, and when they get pulled back, they're all reduced rank, but then they're being summed together, and so the resultant system has full rank, and then we can fully resolve that and get the underlying differential equation. And if we don't have full rank in that final thing, where one, like the system is under constrained. And so there's a question of like, what should it do in that null space? And so ideally you would have a full rank system at that point. And we usually get that by adding some kind of underlying C space term that just like is almost like a diagonal damping matrix in just the system, the linear system. Or you can do something like just choosing what to do with the null space, like getting rid of it or something. But in all of our cases, we try to make sure that the final system is full rank, so everything is specified.
Okay. Thank you, Nathan, for the answer, and thank you very much for the presentation. Thanks everyone to have attended this seminar series. I hope we will see you next time. Don't forget to register to our mailing list or to check on our website for the next seminar series. And I hope you enjoyed this seminar series. Nathan, thanks again, and hope to see you soon.
Thanks for having me.